So when we look at the ways in which we measure carbon dioxide, again, as a scientist, I have extreme difficulty in dealing with these measurements, and I've been practicing science for 40 years, 6 months, 3 days, 11 seconds of my life. And if we look at the black line, that's a chemical measurement, and that chemical measurement of carbon dioxide in the atmosphere started in 1812 and stopped in 1961. And this is where you get a bucket full of air and precipitate out calcium carbonate and measure it. And that's showing us that carbon dioxide has been up and down. And in former times, in the last century, it's been much higher than now. Totally and absolutely unrelated to industry. But on that black line, the lowest point is at 280 parts per million. That is the point that's taken for pre-industrial revolution carbon dioxide. Not the average, you take the lowest possible point. And what that has meant is that you've greatly exaggerated how much carbon dioxide we put into the atmosphere. The bottom red line is carbon dioxide extracted from ice. And as you go deeper and deeper into the ice, you get older and older ice. But what we don't hear much about is that carbon dioxide diffuses and moves through the ice, hence the smooth curve. And the little pink dots to the right are where we measure carbon dioxide from a volcano in Hawaii. We don't hear much about the fact that this volcano is pumping out carbon dioxide into the atmosphere and has been doing it for about 30 million years. But what we do see is that around about 1960, we changed the measurement technique. And by changing the measurement technique, we get a different story. So the pre-industrial revolution number of 280 parts per million was taken by one measuring technique. What we're using today is a different measuring technique. And I say, as a scientist, that's invalid. You're comparing bicycles with grasshoppers. You can't do it. It's invalid. But we hear that figure all the time. We also see that at times we get a correlation between carbon dioxide and temperature, and other times we don't. Now, let us say we take the Hawaiian measurement, spelled incorrectly there, but let us take the Hawaiian measurement. We can see that there's no relationship between increasing carbon dioxide and temperature. Again, we can show this from all sorts of different methodologies. So again, we don't see a relationship between carbon dioxide and temperature. Something else drives temperature. And we can shift carbon dioxide out of the oceans. We're always moving it out of the oceans. And the role of carbon dioxide in the oceans really doesn't get much publicity. But we have a lot of problems with carbon dioxide. We've had times when the planet had a huge amount of carbon dioxide. We didn't have a greenhouse. We've had times when carbon dioxide was very, very high during glaciation and was also very low during hot periods. It doesn't appear to drive temperature, it follows it. We don't have any links that we can use. And we hear some frightening stories about how the oceans are going to go acid and all these poor little shells are going to dissolve and we're all going to be ruined. Well, the problem is that for the history of the planet, our oceans have been alkaline. That's because acid rainwater hits rocks, we get a chemical reaction, the runoff water ends up in the ocean as alkaline material. And new rocks in the bottom of the ocean are constantly reacting with seawater. The only time we're going to get acid oceans is when we run out of rocks. And I think that'll be a Tuesday, about 4,600 million years' time. So we've got an extremely good data set there. We also have the IPC that want carbon dioxide to hang around the atmosphere for a very long period of time. Yet if you start to look at where carbon dioxide comes from and look at all the carbon that we've left on the surface from atomic bombs, radioactive carbon, you get a very different figure. It's about 4 to 5 years. So there's huge discrepancies in the science. And we don't hear these arguments in public. So we've got a few little problems with carbon dioxide. But one of our main problems is with volcanoes. 85% of the world's volcanoes we do not see. And it's the 15% that we see that go into the IPCC models. These are the ones that stick out on the surface and every now and then erupt. We are in a period of quiescence. There's not too much eruption at present. We certainly know that volcanoes change the weather. We know that from Tambora and Krakatoa. But it's the submarine volcanoes we hear nothing about. You got enough shots there, Gillian? Almost, yeah. And it's the submarine volcanoes that we never hear about. Now, submarine volcanoes are when we pull apart the crust of the Earth and we leak out the two major greenhouse gases, water vapour and carbon dioxide. We also leak out a lot of methane and helium. Now, we've got 64,000 kilometres of the Earth's seafloor that we're pulling apart. We are leaking out huge amounts of gas, which is very hot. We're having new eruptions, submarine eruptions every year. And to cool those new rocks, we need to pump through about 10,000 cubic kilometres of water every year. That seawater heats up. That warms up the oceans, which carry 22 times more heat than the atmosphere. That's totally ignored for many IPCC calculations. What is also ignored are the supervolcanoes. We have got very good evidence of supervolcanoes that have created mass extinctions of life. We've got supervolcanoes that are sitting beneath the ocean floor right now. There's a great plumes of molten rock that come up beneath the ocean. And supervolcanoes leak out huge amounts of gas into the ocean sediments and into the ocean water at the bottom. Now, that water is cold, so it dissolves more carbon dioxide. That water's high pressure, so it dissolves more carbon dioxide. That water's still undersaturated in carbon dioxide. We never see the seafloor volcanoes and the carbon dioxide of ocean water as part of the equation. No, it's we humans that are putting carbon dioxide into the oceans, and we'll all be ruined. Now, there's a little bit of literature on this also, giving us the story that in fact submarine volcanoes can drive climate. We've never seen anything in public about the relationship between El Nino events and volcanicity. And as we're having molten rock rise, it pushes apart all the other rocks, so you get swarms of earthquakes. You need to cool that molten rock with circulating seawater, which heats up. That hot circulating seawater is what you need for an El Nino. What else you need is a big low pressure zone. Well, the only reason a molten rock will rise is its low density. And so you get a gravity anomaly above that, and you get a meteorological anomaly above that. So you have this molten rock moving up, heating up seawater, giving you a meteorological low, giving you earthquake swarms, and giving you an El Nino. Now, there's absolutely nothing we hear in the IPCC reports, or do we hear this in public, about volcanoes that might drive El Nino. And there's a reasonable amount of literature on that. We have this problem with people giving us a scare story of our oceans becoming acid because we're putting carbon dioxide into the atmosphere, which then dissolves in the ocean. The problem is that we've had much higher carbon dioxide contents in the past, and the oceans were never acid. And the problem is that if you've forgotten your school chemistry, it's very, very easy to show that the oceans are alkaline for some really simple reasons. And this is chemistry that is very, very elementary. The oceans are quite variable in their alkalinity. Rainwater is very acid, and we just react rainwater with rocks, and we make alkaline water, and we keep it alkaline by seawater reacting with the most common mineral on Earth. Again, we hear nothing about this when we hear the scare of oceans becoming acid. Now we hear these apocryphal stories about the ice sheets melting. Well, ice sheets always melt. They wax and wane. They come and go. And it's very commonly related to the physics of the ice, not to temperature. Because if you've got ice at minus 30 and you have a global warming and the ice becomes minus 20, still ice, not going to melt. And there we have a problem. But if you start to build up the ice sheet, the ice becomes very plastic and it starts to flow down the slope. And we see that in Greenland. We see in Greenland that the ice sheet is accumulating in the centre of Greenland and it's thinning at the edge. Well, that's exactly what happens because ice flows like plasticine. When we look at the movement of the ice, we can see that there's significant changes in the ice, but it doesn't happen in a straight line relationship. It's a surge. So you build up the ice, then it'll surge, and nothing happens for a while. Build it up again, then it'll surge again. And it's a normal way of circulating water between the oceans and the polar areas. So in Greenland, we're actually increasing Greenland by a few centimetres a year.